Welcome to the CAP seminar. Note to self, stop doing CAP seminars during Engineering Open House. I say this every year and I always forget. It's my pleasure to introduce Eli Visbal. I've known him for a long time. He did like seminal work on intensity mapping as a grad student. He did his undergrad at Carnegie Mellon in Pittsburgh. Fun fact, he's from the town where Dave Chappelle moved in Ohio. And then he did his PhD at Harvard, which they call, the Illinois of Boston, with Avi Loeb, who's now internet famous, but this was before he was famous. And then he did two postdocs in New York City, and then moved to University of Toledo about 6-7 years ago. And now he's going to talk about not intensity mapping, but first stars. So take it away. And pizza's late. We'll probably pause when it gets here to eat.
Okay, yep, pause sounds good. All right, thank you, Joaquin, and thanks for inviting me to come give the talk. It's been a great visit. Toledo is just about 5-hour drive, so I kind of have a quick in and out visit, but it's been a really good short visit. And so today I'm going to talk about what our group has been doing on population 3 stars. Okay, very good. Yes, and so I'm an associate professor at Toledo, for those who don't know me. And I'm going to talk about what our group's been doing. So first I just want to introduce the members of our group that have been involved on the POP3 side of things, what we've been working on. And so I especially wanted to highlight the folks whose work I'm going to sort of showcase throughout the seminar. So first is our former postdoc, Mihir Kulkarni, who is a real expert in hydrodynamical simulations, and he's moved on to another postdoc in University of Göttingen in Germany. We have our former grad student Colton, who is now a postdoc in South Africa at Stellenbosch University. And probably most of this work comes with help from Ryan Hazlett, who's currently on the postdoc job market, so he intends to stay in the field. And then also our undergraduate Thomas, who moved on to Michigan State University as a PhD student. And the senior folks I've been working on this stuff with are Greg Bryan, who's at Columbia, and Zoltan Hyman, who's recently moved from Columbia to the Institute for Science and Technology in Austria, sort of across the pond, so to speak. So I want to start out giving sort of the overall picture of what our group focuses on before diving more specifically into POP3. So sort of the big question that sort of drives our work is understanding the first billion years of the universe. And I like to think of it sort of in simple cartoon ways via this diagram, that we have a baby picture of the universe through the CMB, and that tells us about the initial conditions for astrophysics. So, as you folks probably know, the temperature fluctuations, the hot and the cold tell us that the overdensities and underdensities are very tiny, sort of 1.00001 times the mean and 0.999999 times the mean. And so this near uniform early universe tells us that it started out very simple. It was dark matter, gas, radiation, and so we have this beautiful agreement with the standard model of cosmology, and we really understand the initial conditions well. Then sort of by contrast, things get much messier, but beautiful when you say, look at the Hubble Deep Field and you integrate on a blank patch of the sky. You see by let's say redshift 6, which is 1 billion years after the Big Bang, you see even in a tiny patch of the sky, tens of thousands of galaxies, and all sort of nonlinear physics, great complexity. And our group's main interest is trying to understand how did we go from these very simple initial conditions to the complexity that we see 1 billion years after the Big Bang, which is about a redshift of 6. And so here's that cosmic timeline where we see at the CMB gives us a clear picture, that baby picture at recombination of hundreds of thousands of years after the Big Bang. Then we see many galaxies sort of 1 billion years later. And Webb is pushing into bright galaxies up to very high redshifts currently. But our focus is our group likes to think about the emergence of the first stars, cosmic dawn, which is hundreds of millions of years, down to sort of the end of reionization, which occurred probably at this billion year marker at about a redshift of 6. And so what are the big questions that we're interested in? Well, today I'm going to mainly discuss the first stars. So we're interested in how did they form, what were their properties. Another open question that's highly relevant is that even at these, it relates to POP3 stars, and I'll hopefully have time to get to, which is we know supermassive black holes are sort of ubiquitous features of massive galaxies today, but we don't actually know how they form. So what were the seed black holes that grew into galaxies we see today? So that's another sort of big picture question that relates to the high redshift universe. And finally, how did the process of reionization occur? So we see the CMB up here because the universe recombined, the gas was neutral, but then we know by redshift 6, most of the intergalactic medium is ionized. And how did that process, how did that last big phase transition in the intergalactic medium occur? So those are sort of 3 questions we're kind of focused on in our different groups' efforts. And my reason to why they're interesting is because answering these questions will fill in sort of a gap in the cosmic timeline. Because like I said, we have really great understanding of CMB. Of course, we always want to get more modes, but and galaxies in the local universe are easier to see. But this part in the middle, we'd like to fill in the story of how the universe evolved. Studying things like POP3 stars tell us about the earliest stages of galaxy evolution, and as I'll mention, potentially might reveal new dark matter physics. And it's also interesting because there are lots of current and upcoming instruments that will allow us to probe back farther into the early universe. So Webb is already doing this, very high redshift observations. 30-meter class ground-based telescopes, when they're built, will continue to help open this window. And line intensity mapping, including things like 21 centimeter, which this is Hera. Is trying to observe the early universe through line emission from the intergalactic medium. And so these new observatories give us deep observations, which let us see earlier in the universe. And our sort of overarching goal as a group is to try to do the theory that will help maximize the scientific return of all of these different instruments. So we use different tools, but we're basically a pure theory group. So that's just an introduction to what our group at UT Toledo does. In today's talk, I'm going to focus on the POP3 work we've been doing recently. And the structure of the talk is, first I want to give a little bit of background on population 3 stars. Then I'm going to move on to some of the modeling efforts that we've done to understand sort of how the abundance of, like when and where POP3 stars and how this evolves over the history of the universe, and some of the challenges there and different types of simulations we've run to overcome them. Then after I talk about the modeling, I'm going to talk about 2 specific observations we've made predictions for. One is this highly lensed Webb candidate called LAP1b, and LAP stands for lensed and pristine, and we really think it could be a POP3 source. And then I'm going to talk about how we can learn about POP3 stars by their chemical signatures left in quasar absorption spectra. So I'll discuss that. And then hopefully I will have some time at the end to describe how our POP3 work also connects to formation of supermassive black holes and what's known as massive or heavy seeds, where you actually make a 10 to the 5 solar mass star, so a supermassive star, that then it collapses into a black hole, and this might explain the early emergence of supermassive black holes well, maybe everywhere, but in particular in the early universe, where it's challenging to understand how they got so massive so quickly. So that's the roadmap of the talk, so let's jump right in. Okay, so in terms of background on population 3 stars, what is a population 3 star? Well, really, it's just defined as stars made from primordial gas, left over from the Big Bang. So you're talking stars that are essentially just made with hydrogen and helium, though you may find, although a little sprinkling of metals is considered okay. I'm not going to go into the details, but we generally think of there being some critical metallicity above which the fragmentation and formation of the stars changes in some noticeable way, and then that's the threshold at which we'd call them no longer POP3, but POP2, and their IMF would probably look much more like what we observe today. And yeah, so the theoretical predictions are that because you don't, but for the most part, just think of them as extremely or zero metallicity stars, extremely low or zero metallicity stars. We don't have necessarily definitive observations, but we're getting closer, like what I'm going to talk about later today. But there has been theory that's been going for a long time on them, and some of the main predictions are because you don't have metals, the gas has to cool via H2. And the first halos in the universe at very high redshift that have enough H2 to cool are sort of very tiny halos, 10 to the 5, 10 to the 6 solar mass dark matter halos that we call mini halos. And that's about a factor of 1 million less than the Milky Way's halo, so they're tiny. And we think the difference in cooling leads to them being more massive. So if you have all these metal species and molecules and things, you have more channels to cool. The gas can get to lower temperature, and then the gene's mass is lower, you get more fragmentation, and you make lower mass stars, whereas if you just have the H2 cooling's not as efficient. The generic prediction from simulations is that you get more massive POP3 stars with maybe 100 solar masses being typical or something like this, or 50, but that is still a matter of debate. We don't know exactly what the IMF looks like, the initial mass function. So that's some of the open questions are their IMF. It'd be great to know. We're trying to work on understanding how does their abundance evolve over time, how do they impact the IGM, and they're important to understand because they'll teach us about early stages of galaxy evolution as well as potentially dark matter physics, which I wanted to show with this slide. That this is maybe in a cosmology class you've seen Preschecter theory or Schecht-Torm as it's known. It's the halo mass function. One can sort of analytically figure out the number of halos you have as a function of halo mass. And so what you might do in a galaxy or cosmology class is derive these curves in lambda CDM that they basically tell you have lots. I forget, this is at 100 million and 500 million years. I forget, maybe redshift 20 or something like that, or 10. This is at high redshift, but it happens at lower redshift as well, that you have many small halos in lambda CDM and fewer orders of magnitude lower massive halos. So I think this is redshift 20 that you go all the way from 10 orders of magnitude as you go from mini halos to 10 to the 8 halos. So big halos are rare in lambda CDM. And some of the alternatives of theories of dark matter, besides say a WIMP, the simplest thing you could do could be something called fuzzy dark matter. Warm dark matter operates in a similar way where you basically suppress small scale structure formation, and then you would basically have the physics of the dark matter would eliminate very low mass halos, and these are the low mass halos where it depends in say fuzzy dark matter, it depends on the particle mass, and there's different parameters that might go into these things, but it's just a property of some theories of dark matter that you shut down small scale structure, and some of the smallest small scale structure in cosmology you could examine would be the sites of these first stars. So we want to make really good predictions in lambda CDM. That way if we go out and we see no evidence for stars forming at high redshifts in these little abundant halos everywhere, it would tell us that maybe dark matter physics is shutting down the formation of just dark matter structure on small scales. So that's another motivation in just understanding these astrophysical creatures. Yeah.
Why is specifically that mass range of halos where the first stars are?
Yeah, it's a good question. I don't know if I put this just for kind of illustrative purposes. This can totally move left or right depending on a free parameter in the fuzzy dark matter model. Basically, the way it works is fuzzy dark matter is a theory where you make the mass so small that the de Broglie wavelength becomes like astrophysical scale, and then basically due to the uncertainty principle, you can't like shove a bunch of material at low momentum and in a specific position, because then you'd know the position and momentum, and so you can't squeeze together a small little halo, and it totally depends just on the mass of the particle you pick. And I think the strongest limits are from the Lyman-alpha forest, but I don't think that this is, I'm just trying to illustrate the concept. The idea would be if we see these, it would make it so that we know the particle is so massive that the cutoff would happen even farther over here. So basically, that's why if we measure these things, it'll be able to tell us where that cutoff should be. But we don't actually know. So sorry for not being clear about that. Okay, and so there's different ways we hope to observe POP3, supernovae, gravitational waves from their remnants merging together, looking at their impact on high-redshift galaxies, maybe chemically. There's a whole industry of looking at extremely low metallicity stars in the Milky Way to see the second generation of stars form from supernovae ejecta from POP3 stars. You can use that to study POP3 stars, 21 centimeter. So there's lots of different things. I'm going to talk about direct observations with Webb and this damped Lyman-alpha absorption systems later. So even more than what we have there. Okay, so that is my sort of lightning review of what I think the important things are to think about when it comes to POP3 stars in terms of background. So now I want to move on to like what our group has been doing to model POP3 stars with the ultimate goal of making contact with observations. So one of the key questions the quantitative questions we wanted to address, this work is a few years old now, but it still connects to everything we're currently doing, which is understand quantitatively what is the halo mass where POP3 stars actually first occur. And in the physics, you can just think of is you have a dark matter halo, gas collapses in. Initially, it's pressure supported, and you need to cool that gas for it to have runaway collapse form stars. As I mentioned, that happens via rotations and vibrations of H2 molecules. They emit radiation. That radiation leaves the system. Then you can cool and make stars. And so that's what we're trying to understand. There have been simulations and analytic work that suggested that this happens around 10 to the 6 solar masses at high redshift. But basically, prior to some of our work, all of the physical effects hadn't been put together, which I'll describe some of these important physical effects. And it was really time to have an updated, more accurate, because we didn't change the overall roughly speaking, that is 10 to 6, but you actually want to know precisely what this minimum mass is because it affects their abundance strongly. Because if you think back to that halo mass function, if you go down a little bit in mass, you get way more halos. So when you go through the calculation for the abundance of POP3 stars at different redshifts, in the number of halos cosmologically, it's very sensitive to a factor of a few can make a significant difference in the abundance of POP3 stars you get. So there are two effects that we put together for the first time in some work led by Mihir Kulkarni, my former postdoc. The first one is this idea of Lyman-Werner feedback. So Lyman-Werner photons are in this energy range, 11 to 13 eV, and the important part is they photodissociate H2. And so this leads then to self-regulation of first star formation. That what happens is that the first stars turn on, they grow into larger metal-enriched galaxies, but all of those stars that are forming emit Lyman-Werner radiation. Then these little halos that would have been the sites of additional POP3 star formation in a separate halo, some cosmological distance away, they get hit by Lyman-Werner radiation, which then photodissociates the H2 and makes it harder for them to make POP3. And so effectively what happens is that as this Lyman-Werner radiation builds up in the universe, you need more massive halos in order to have enough dense gas to make H2 and cool. So it's basically an effect that raises the minimum mass of halo that you need to make a POP3 star because it's a negative feedback kind of. So that's effect 1. Effect 2 that we also wanted to simultaneously include was something called the baryon dark matter streaming velocity. And it was first identified back in 2010 by Dmitry Selyakovich and Chris Harada. And the idea is that basically prior to when we see the CMB, prior to recombination, the photons and the gas were coupled, but the dark matter was not coupled to the radiation. So the dark matter can sort of gravitationally fall into, clump more in overdense regions, whereas the gas is supported by the pressure of the plasma, the radiation of the plasma. Then eventually the gas decouples from the radiation at recombination, and it starts to fall more into the potential wells. But because of this difference in history prior to recombination, there's a relative velocity between the dark matter and the baryonic, the dark matter and the gas. And that relative velocity is enough to change early star formation. And so this is like the cartoon picture of what happens. It's just you have a dark matter halo that starts to form, and if you're in a region that has a high, sometimes it's called streaming velocity, the gas takes longer to settle down into the halo just because it's whooshing past it. And sort of if you look on large scales cosmologically, this is like hundreds of megaparsecs across. You get sort of coherent regions that are about 100. They're actually similar to the baryon acoustic oscillation scale, that you get these large 100 megaparsec regions that you'll have hot spots where all of the structure in there has a high streaming velocity, and then cold spots where you have a low streaming velocity. And then those hot spots, you delay star formation because it's similar in Lyman-Werner in the sense you have these two effects that both delay star formation. And so the work we wanted to do that Mahir led 5 years ago now, but as I said, kind of feeds into things, was to run simulations of in which halos these formed, including both of those effects simultaneously, which hadn't been done. And he used the ENSO code, which is a hydrodynamical code, and we ran cosmological boxes, starting from cosmological initial conditions, following gas, and then identified the moment right before star formation when the gas was starting to, and we include all the chemistry and cooling in that gas. So you see how much H2 builds up and when does it cool, and we basically then could see at what halo masses you're forming. The runaway collapse is starting to occur, and we know star formation would occur then. And so here's an example. And then what we did was change the Lyman-Werner background, change the streaming, and do different combinations in a grid of all these different possibilities to understand quantitatively, including all this physics, when the first stars form. And here's an example of if you take a weak Lyman-Werner background, you have high H2, and then you get dense gas in the clump in the middle, and the gas is able to cool, and stars would form that clump. But if you turn up the Lyman-Werner background, then you get several orders of magnitude less molecular hydrogen, so the gas doesn't cool and you don't get star formation. And so we basically systematically did this over a large number of combinations and ended up with results that look like this, of what were the dark matter halo masses when the first POP3 stars formed as a function of redshift when you look at different Lyman-Werner strengths. So I wouldn't worry these are in these units that are where 1 is sort of the typical background in the high redshift universe. So that's what J21 is. It's like 10 to the minus 21 ergs per second per centimeter squared per hertz per radian. Oh, should we take a little break? Let them set up. Okay. And so we computed the halo masses, including both of these effects. And yeah, we basically, now anyone else who wants to take this and say put it in a different model, we've done fitting functions that we give you what the minimum halo mass when POP3 occurs as both a function of the redshift, the intensity of this Lyman-Werner radiation, and the magnitude of this baryon dark matter streaming velocity. And yeah, we basically found that the masses were a little bit lower than previously thought because of some H2 self-shielding that wasn't properly included in some of the earlier work. And And basically, before we put this out, people by necessity were each effect had been studied individually. And so people were saying, if one of the effects increases the minimum mass by 2 and the other effect increases it by 2, let's just say now it's going to be 4 that you increase the minimum mass by, just because that's all they could do. But we realized they do work together, but not in a way that's weaker than being multiplicative like that, is what we had discovered. Okay, so that is some of the hydrosim work that Mahir led in our group. But this brings us to another challenge. It is simulations are very computationally expensive. So these are the Renaissance simulations, which followed early star formation, including POP3 and transition to metal-enriched stars. Hydrodynamical simulations with astrophysics can include all of these important feedback effects that we want to understand, like ionization of hydrogen, metal enrichment from supernovae, this Lyman-Werner background I was just describing. And we need this to understand how stars form and evolve to make predictions. The problem is they're very expensive. I mean, they're great in that following physics with high fidelity, but they're very numerically expensive. So the Renaissance simulations, which was a few megaparsec box, took millions of CPU hours to run down to redshift 10, which isn't even the end of reionization, which is where we want to actually, as I'm going to get to for some of the observations, we want to look at lower redshift. And it takes millions, and there are still uncertain parameters you have to put in, like the IMF of POP3 stars is put in by hand, for example. So you can't explore parameters, but even with, there's subgrid models that you make choices, you only get to look at one choice. And you can't go low enough redshift because it's not computationally fast enough. And it's hard to do large volume. So they're great for physics, but they're a little bit limiting in, and actually even these didn't quite resolve the smallest mini halos that POP3 stars form in, just because that's another challenge. So all that to say, they're extremely useful, but there are challenges with running simulations. Should I just continue? Maybe we'll just continue. Okay, so it would be nice to have simulations combined with some complementary approach, which is kind of what we've gone towards in our group. That we've developed this semianalytic model that basically takes cosmological n-body simulations, gets all of the dark matter halos in those simulations. We just run these gadget boxes, use the Rockstar Halo Finder, it's publicly available, find all the halos in their merger trees, and then we use analytic prescriptions to figure out where the POP3 form, when they transition to POP2, and then we've put in all of the important feedback processes we can think of into these semi-analytic models. So we include a model for the early stages of cosmic reionization, metal bubbles coming out from galaxies, this Lyman-Werner feedback and its fluctuations throughout our simulation boxes, the streaming velocity I mentioned. And so then you basically can follow through time, say this is a few megaparsec box, and each clump or each dot is a halo where you either have a metal-enriched galaxy or a POP3 galaxy that's just formed. So this is at redshift 8, that you get a couple POP3 formed at this time, and a bunch of other halos that are more developed galaxies. And then we have our sort of spherical cow model of how the metal bubbles, supernovae winds blow from everything. And the same for ionization bubbles, Lyman-Werner radiation, all these important feedback effects, how different, yeah, question.
How many POP3 stars in a mini halo would go supernovae until the stars forming would now be POP2 stars? Should I be thinking of it as like?
That's a good question. That's how I think of it. I don't think we fully have a precise answer on that because it's hard to simulate, I think. And it depends on kind of the metal mix. You can imagine you have some pockets of that you have metals, but then the mixing isn't perfectly efficient. So you have some so I think of it more on the few, but this is still an open question. I think it needs, I don't have a perfect answer, but it's a very good question. It's one that I actually want to run better simulations for. And so we have this, that basically now we have something that we can run what would take millions of CPU hours to run the hydro. Now we can run in like 10 CPU hours. So you can run many models very quickly. And our strategy then is not stop here, but try to calibrate these to the hydro sims so that we can hopefully get the best of both worlds. So that in our group has been like the approach that we've been trying to take, where this has mostly been led by my PhD student, Ryan. And so he did a study that he published last year where he looked at galaxies in the Renaissance simulation that I just mentioned, mapped out in this case I'm showing the POP2 star formation history of one of these galaxies. And so and he noticed something that like was popped, and then basically the plan was to look at many galaxies in the simulation and then come up with a scheme that you can do it semi-analytically and really recover what's going on in an accurate way. And then we can run many more SAMs that are guided by the hydrosims. And so when he performed this study, the thing that he really discovered was that below a certain mass, which ended up being, I don't want to get into the weeds too much, but basically sort of 10 to the 8 halos, solar mass halos around there. It's a bit redshift dependent, but below that you had this very bursty mode of star formation where you would have like basically the gravitational potential well of the halo is not sufficient to like recover quickly. That the stars go off. This is the POP3 stars as a function of time in one of these galaxies in Renaissance. You make a bunch of stars, then it has a quiescent period when nothing happens. Then it blows then it has another big starburst, then nothing happens for a while. And then there's a certain mass where you just get more smooth, steady star formation. So we modeled this with like this two-part. We calibrated we figured out what the statistics were of the bursty bit, and then we came up with like wrote down some physics equations where we basically, differential equations where we assumed the star formation is proportional to the amount of available gas. The star formation rate is proportional to the amount of available gas, and we could calibrate that equation to what we saw in the simulations. And so here's an example of then for different halos in our model, it's like stochastic in the sense that it draws from the distributions of what the simulations tell you. So you can take for a single halo in our SAM, it could give you many histories, and they won't always be, you roll the dice, pick a different random seed, you get something different, but they qualitatively follow what you get for the star formation history in the sims. And then if you look at global properties, say the metal enriched star formation rate is a function of redshift in Renaissance. In their it's about 5 megaparsec box, they got the black line. And then when we take the same dark matter halos and apply the SAM, we recover, because it's calibrated at some level, I mean, this should happen, then we get the same star formation history, both in POP. This is star formation rate density as a function of redshift for POP3 and on the right and POP2 on the left. And we get reasonable agreement. And so anyway, this allows us then to extend to lower redshifts. And so this is what we've learned. And we can check lots of different uncertain model parameterizations related to POP3 stars. So in this plot, I've taken our fiducial model, which is black. It's kind of buried a little bit. And the top set of curves are, so this is like the Madal plot, basically, sometimes called the star formation rate. Density is a function of redshift. If you go way out here, you'd be at cosmic noon, where it would peak and go back down. So we're looking at sort of the early stages of that Madal plot. And then this is the upper set of curves that are solid are POP2, and the dashed lower ones are POP3. So from our models, you can see basically how long does POP3 persist. And in our fiducial model, you see in most of our models, POP3 quickly becomes the lesser dominant source, but it doesn't disappear. Like you basically get this slow and you get more and more POP2 over time, but you have this like kind of flat, slow and steady burn of POP3 forming throughout the universe. Basically what's happening is in sort of void regions where metals haven't reached them, you still get new pristine pockets of POP3. And so This is like other groups have found similar things. It's a pretty robust prediction from cosmological simulations that you expect POP3 to continue late. Exactly when it cuts off, we don't know. We need to run these longer and figure out, is redshift 3, is there still some? I don't know. It definitely starts to drop off towards the end of reionization, but it doesn't go to like 0.
Is that, in your simulation, is that the first star there at 32?
Yeah, so this is the first star, and that's set by the fact that we've used, to make this plot, I've used 10 3 megaparsec boxes. But if you had a bigger volume, you would, so I wouldn't trust anything beyond like here is not quite accurate because it's like sampling a smaller volume than the real. But I do have thoughts of basically making a really big box and sampling different patches in a way to do the cosmic variance correctly. But yeah, so we can vary things like the efficiency of POP3 star formation, this critical metallicity where you transition from POP3 to POP2, which are metal-enriched stars. An important parameter ends up being this T delay I'm going to get to revisit later. That's the delay time between when a POP3 supernovae goes off and then it takes the gas to settle back down and transition to POP2. And so that's one that's dramatic in that you make POP3 in that purple curve out here, and then you have a long pause, so POP3 actually dominates for a longer time before POP2 is allowed to turn on, that kind of thing. So that's the advantage of these models, that you can check the whole parameter space very quickly, and you can simulate lots of n-body simulations, do big boxes, and then it's much easier to connect with observables, which is really our ultimate goal, right? And so that's what we're finally getting towards, that concludes sort of what we've been doing on modeling part of the talk. So now I want to talk about what we're doing to apply it to observations. And it's really, I think, the combination of hydrosims informing these semianalytic models, or SAMs, that let us kind of trust our models to an extent that you do the sims, but also go to low enough redshifts, have large enough boxes, check parameter spaces that we can connect with observations. So I first want to talk about this web source, LAP1b. It's at redshift 6.6, and it's basically this little clump that is sitting. This is a gravitationally, it's gravitationally lensed in a cluster, max 0416, and there were basically 3 blobs seen, and it was found that these 2 blobs are from the same object, which is the one of more interest, LAP1b. And so according to their lensing model, it's magnified by a factor of about 100. So it's really allowing us to see something faint due to the cluster lensing. There's no continuum measured, but they've seen various emission lines, including Lyman-alpha, H-alpha, and some metal lines. And you may say, wait, how are there metal lines if it's POP3? Well, if this is POP3, it's actually the case where you have a POP3 cluster, but one of them has either blown supernovae and contaminated the gas around, or stellar winds from the stars have blown off onto the surrounding gas cloud, that is where the emissions actually coming from. It's nebular emission from that gas around a small cluster of POP3 stars, if that's the correct interpretation. And also looking at the H-alpha to H-beta ratio shows that there's no dust, negligible dust emission. And so this, and Vanzella et al. And Nakajima were the observational papers that first put this out. And we got really excited about this object. Yeah, question?
Sorry, I'm just having a hard time understanding how you're extrapolating that this might be a candidate POP3 star if you're seeing other metal lines in.
Yeah, very good question. Let me elaborate on that. So this shows the strongest evidence that it's POP3. So the idea is, it is very low metallicity. So it is lower metallicity than pretty much anything else that Webb has seen at high redshift. So that's helps push in that direction. But no, it's not truly metal free because we've detected metals there now. So it would have to be that in it's a timing issue, but we've done some calculations. I don't think it's unreasonable to expect that the lifetime of a massive POP3 stars would be a few mega years, and over that time you form some. One is one, maybe some formation continues, one or multiple spread some metals in their vicinity, and then you still have POP3 alive and shining radiation on that now metal-enriched gas around the POP3. So that's the picture that you have, that you still have some surviving POP3 stars that were formed at extremely low metallicity or metal-free, and they've just started the process of self-enriching their environment, and we're seeing that system, that a gas cloud surrounding POP3 stars that has been self-enriched a little bit.
But the argument comes from the fact that
It's incredibly low metallicity, and the other part of the argument is this, that from line diagnostics, it's not consistent with POP2 stars. And so I'll show what I mean. That basically, they've made these C4O3 line ratio comparisons, and because you need more energy to ionize carbon knock off the electrons to get to C4 ion, you need higher energy photons, which basically POP2 don't make. You need massive POP3 stars to get that ionization species in your, yeah.
So am I interpreting right? You're saying that it would need to be a high mass POP3 star that forms in a cluster in a mini halo, or like what size, spatial, and mass extent are we talking about for the host environment that hosts multiple massive stars?
So, good question. Yeah, so I think this diagnostic is telling us about the mass of the stars themselves, that we do think it could be consistent with like a top-heavy IMF and not consistent with normal metal-enriched stars. So that's point one. And then I'm going to get to your other question very soon of that. This tells us about the stars, but then we've thought about, basically to get to the short answer is that mini halos you don't expect because the Lyman-Werner background is high enough at that time. You get to atomic cooling halos, so we're thinking it's basically an atomic cooling halo that's more like a few times 10 to the 7, 10 to the 8 solar masses is the halo. Okay, and so we saw this, we got very excited about it, and we said, wrote a short little letter where we said we think this is the first system consistent with POP. We didn't say it is POP3 stars, we just said in the ways we were looking at and thinking about it is consistent with our theoretical expectations for POP3 stars. And we had three sort of main points that we considered the classical theory of like what had been established in the literature, that basically depending on this Lyman-Werner feedback and other things, POP3 stars are, and what we meant by classical is there's some recent work more about like inefficient mixing of gas where you might have pristine pockets in big galaxies. That we're not thinking about. We're thinking about more when you really have a system that it's making stars for the first time and it's POP3, not some sort of mixture. And those are first expected to form very initially 10 to the 5 or so solar masses, but by later redshifts, like where LAP1b is, this Lyman-Werner feedback effect I discussed should really crank it up closer to the 10 to the 8 solar masses. So that's a prediction that's been made a while ago. Simulators have not converged on an exact IMF for the POP3 stars, but in general they tend to include massive stars and often like a logarithmically flat IMF, where if you look at like the number versus log of mass, it looks flat and has some cutoff at very high mass, but like 100,000 like solar masses could be a very flat IMF. And also most of the cosmological simulations find that you quickly transition to POP2. So the other candidates that were out there all had line luminosities that required you to have like 10 to the 5 solar mass of POP3 stars, which we were always, I don't know that that's impossible, but it would have been a bit on the high side. It was always uncomfortable to me. The other sources out there seemed, many of our simulations, like Renaissance and EOS is like a next generation kind of one, they all show a faster transition to POP2, and you don't get this big of sources. But that was an exception here. As I'm going to get to, it turns out that it's because it's lensed so strongly, it might only be of order 1,000 solar masses of POP3 stars So it hit all, and so the line ratios told us that it's probably massive stars, and then I'm going to get to the other points. But yeah, basically these 3 points, we saw it was the first one that really looked very consistent with all of them. So here is what we thought about the stellar mass, that you could just do, we just did the very simple calculation where we looked at the stellar models from Scher et al. And figured out how many stars do you need to make their best measured line, which was the H alpha. It's a recombination line. So you just have to assume an escape fraction of the ionizing radiation. We assumed 10%, which could vary a little bit, but roughly speaking, it should give us the right order of magnitude of basically how many ionizing photons from those POP3 stars are deposited into the nearby gas that then cause recombinations leading to H alpha. And so from that, we could see basically how many stars were required to make that line. And what I've plotted here is the total mass in POP3 stars in LAP1A, as if you made the simple assumption that all the stars had a common mass, like they're all 100 solar mass or they're all 40. This x-axis is what that common solar mass is for an individual star. And on the vertical is the total stellar mass. So you can see basically to get the right line luminosity, if you had like, what is this, 250 solar mass stars, you'd need like 3 of them. So you could have 3 250 solar mass stars, which is pretty incredible to make that line luminosity, if it in fact is lensed by a factor of 100, magnified by a factor of 100. So because the more massive stars are more efficient at making ionizing photons, you need a little bit more mass in stars if it's lower mass. So if they were 20 solar mass, or let's say 30 solar mass stars, you'd need about 100. So you could have 100 POP3 stars that are all on the scale of 30 solar mass to make that recombination line. So anyway, this is basically then the evidence that we're like, okay, wow, this is only roughly speaking 1,000 solar mass, which is 2 orders of magnitude lower than some of the other candidates that have been proposed with Webb. So we thought this is pretty cool, and it's more what we in line with simulations. Yeah, Matt.
Does it change if the mass distribution is not uniform?
Yeah, this would be the mass that was in massive ones, I guess.
Okay.
If you had one that wasn't as steep or as flat, you could have like a higher total mass where a lot of it was in like low mass stars, I guess. So this is a pretty simple calculation. But
Thank you.
okay, and so what about metals? This goes back to the question that was asked earlier. Let's see. Like I said, it's low metallicity, but not zero metallicity. So this gives the oxygen abundance compared to the hydrogen. You see these are other Webb galaxies, and it's way down here. So it is a very not metal enriched source, which that's why we were thinking POP3 to begin with. But then I always thought before this, I didn't really think of this possibility of pre-enriching themselves, their own environment. I thought, you just see them POP3 and that would be it. But this motivated us to think about this a little bit more in pretty simple, almost back of the envelope ways. And and it really could be POP3 stars that just a few have recently enriched their environment. So it would just take, basically with some diagnostics that the observational paper put out, they said they needed about 10 solar mass of oxygen in that gas to explain the different metal line strengths. And this could be a single POP3 supernovae, or if you have rapidly rotating POP3 stars, winds blowing off of them for some fraction of the lifetime of the stars would give you that much metal oxygen. So that's the amount of oxygen is not a problem, really. I mean, one POP3 star does not seem crazy at all to me, although we haven't simulated like the full distribution of that. And then on the other side, the original group that put it out observationally said it had this line width of 58 kilometers per second, and they attributed that to the dynamics of the gas orbiting in the halo. But I did the calculation, and you need a very massive halo, much more massive than like where we expect POP3 stars to form. So our interpretation is not that it's the rotational velocity, but that it's actually comparable if you look at simulations of just the radiation pushing out gas from a POP3 star gets close to those velocities, and supernovae, even if you look at in the ISM in local galaxies, can be higher velocities and slow down to that too. So it could be simply that the stars, either through their radiation or through a supernovae, have accelerated the gas in such a way that it broadens the lines, which is much less than you actually. It's still in such a small halo. The rotation would not give this high of a rotational velocity. Yeah.
How does this metallicity from James Webb, I know it's a very different survey, but like compared to some of the metallicities of super metal poor stars in our galaxy?
I mean, that must be what these gray points. So, I mean, these are redshift 0 ultra faint dwarfs. So
okay.
They must be kind of. I'm not sure. That's not exactly the halo stars, but yeah, maybe on the same. Okay. I'd have to check. But yeah, they get very metal poor. If you look hard enough, you find very. But that's a little different because our galaxy overall isn't metal poor. That's a single star. So you could have that's like probing the tail, where for these galaxies, it's like you're averaging over everything. Okay, so then the final thing we did with respect to this was that, okay, this is really interesting, but do we actually expect to find this? So we took those semianalytic models I was talking about, and we basically just asked, what's the abundance of POP3 stars that, taking the timing of their lifetime, that are into account, so that you, like, if you looked in some volume, how many are currently on at some redshift? And so we looked at that. That's the top curve. This is the number density as a function of redshift. And then we said, okay, well, how faint are they in our simulation, and how bright would their H-alpha line be? And we'd said, oh, well, given Webb with strong lensing like this, Webb would be able to see them out to redshift of about, this is the second panel is the H-alpha luminosity we'd predict as a function of redshift. You should be able to see them about redshift 8 or so. And then we said, let's take the area of a gravitational lens like this. Actually, we chose the exact one, max 0416, and I found a table where they said, what is the area where the fraction of that, what is the area of that lens that is magnified a factor of 30 or higher? Then I use that area to figure out what's the cumulative number of POP3 stars you would see as a function of redshift if you started searching from them. And we found that at Z lap 1b, that's about when you expect to find one. So, I mean, that's not like, yes, it has to be true, but it just shows plausibility, yes. Like there's no reason. Our prediction, and I did not change any of the parameters in this model after the lap 1b paper. I went back to my fiducial model that we had published years before, ran it through, and we do get of order unity predicted behind here. So I think that's really the punchline why we decided to put out a short little letter, because we said, I would have thought maybe the POP3 are too rare and this would be hopeless, but I think if you look at clusters, our prediction is you will find some, if they're as efficient, if making POP3 clusters of thousands of solar massive stars, you should look at, and you look at some clusters, you should find some, is our prediction. Although, like I said, we need to keep doing better simulations, refine some of the models, but in different parameterizations, it's not like we did not fine tune this. This was just the fiducial best guess model. Okay, so, I'm almost out of time, so I guess I probably won't get through this topic. I can just mention in like 2 minutes this other thing that we've looked at recently. I knew I made too much. But basically, another probe we've been interested in is look at quasar spectra and then see, like you can do things like the Lyman-alpha forest. People look at damp Lyman-alpha observers, which is defined as a certain column density of hydrogen that you see in the spectrum, things that correspond to gas clouds clumped along the line of sight. And so basically, this has recently been done instead of Lyman-alpha, you can use this oxygen line. And because oxygen is less plentiful, it doesn't saturate as much. So you can still do it higher redshift, because it gets very hard to do when you get tons of, the whole spectrum's just pure absorption everywhere in Lyman-alpha if you go to too high of redshift. But O1 allows you to do it. And so this group, Sedini et al., had put forward a list of about 30 systems around redshift 6 that displayed kind of weird metal abundances that they claim could be related to POP3. And it was related to things like the CO that they see this jump up in CO abundances of some of these clouds that are probed by the quasar absorption systems. And they basically said, okay, well, in some of their models that weren't really cosmological, but they just assumed a single POP3 star with different yields, some of these points corresponded to their models with POP3 and not just POP2. And so I wanted to ask the question, if we run it through this semi-analytic model, do we predict the abundance of these systems that they see in these quasar sightlines? And so because I'm basically out of town, I'll just get to the punchline there. We ran simulations, and this is the punchline, that basically the number of DLAs that they measured as a function of the CO metal abundance ratio in those DLAs, we predicted for different ones, parameterizations of our semi-analytic model, which are the solid curves, and then the ones with the stars with the error bars are the number that they actually measured. And we found that, for our fiducial model, actually we under-predicted quite substantially the number of these high CO systems. And we found out one way to fix that was to increase this delay time between POP3 and POP2. So what happened then is you'd make POP3, then it would be a long time before the POP2 turned on and polluted and washed out that signal. So the signal survives longer in more objects because you don't wash it out as quickly. And so we found that then you could get good agreement with the abundance of the systems that you would infer from the number of quasar sightlines they looked at. And so basically, I want to conclude this by saying there's more work to be done here because there's a lot of physics that goes into this modeling, but I do think it could help us put constraints on the properties of POP3 stars. So anyway, I'm basically out of time, so I'll just go to my conclusions. Unfortunately, I can't talk about black hole seeds, but you can read a sentence about it or maybe ask for me before I head out. But thank you, everybody, for your attention. If there's any time for any questions.
Hi, thank you so much for the talk. So I had a question about the work modeling this sort of mass cutoff where your star formation histories go from being really bursty to being more smooth. I was wondering if you found that mass was similar to some of the masses that have been found where you see bursty star formation at high redshift or in dwarf galaxies in the local universe.
Good question. We did not compare it to observations too much. I mean, I guess it's hard with an observation because you don't have the full, I guess you can reconstruct histories, but no, we didn't look at those. I don't know if I can give you too accurate of an answer on that. I would say the scale is quite small, so 10 to the 8, it's, to be more technical, it's like there's this mass scale that's basically like the genes mass that there's like a time, it's sort of like a time-dependent genes mass that sometimes called like the filtering scale, that basically it's like if the halo gets big enough, once the gas is photoheated to 10 to the 4 Kelvin, the gas can still be captured gravitationally by the halo. And so that's about the scale when, that's what we think is driving it becoming more efficient around there, which is sort of like 10 to the 8 or 10 to the 9 halos at high redshift, which sounds like right around maybe it's a small dwarf galaxy. I think maybe quite small, but so it might be, if that puts it into like sources you're thinking of that.
Yeah, thank you for the talk again. So you mentioned at the beginning sort of these instruments that are designed to map global parameters of the epoch of reionization. So like Hera, for example, these line intensity mappers and stuff. I'm wondering how those experiments measuring more global parameters, what they can tell us, if anything, about the more like specifics about POP3 stars and how they complement each other at all.
Yeah, good question. So I think it depends on what the signal actually looks like out there, but I didn't share it today, but my former student Colton has worked on like 21 centimeter predictions out to very high redshift, from like redshift 40 to 15, and up until like redshift 20 or something, POP3 is dominating. And so you're only going to see how those stars influence the IGM in 21 centimeter, but I do think you can put like any microphysics you put in the large scale simulation on small scales is going to impact, basically there might be degeneracy. We still have to work out all the degeneracies and things, but at some level, you change the POP3 stars, they're going to change the X-ray heating, because there's all these features in the 21 centimeter signal of like, you have this there's all this, the Lyman-alpha coupling, and then the X-ray heating, and there's all these things that are very rich in physics, and the problem is disentangle. I think we can, basically. Sorry, I can't give you a plot or anything, but yeah, the information is there. It's just there are going to be degeneracies, and you have to try to like marginalize over everything you can and stuff.
I'm just wondering about the delay time. That's a neat thing. I would have guessed that it would depend a lot on the mass of the halo that it was happening inside. Do you figure that that's true? You gave a sort of typical number, like 50 million years.
I think so, yeah, I think you're right. That's probably a shortcoming of our model at this point. We put in a constant delay time. The simulations we have that actually show this, that we've been starting to try to measure it from the simulations, you actually get a really big spread in them too. So it's not only, the halo mass must matter, but there are other things that matter too, because for halos of a given mass, you get a huge spread. Like you get some that are 10 megayears, some greater than 100 and never come back. And yeah, I think that's one factor, but that we aren't currently really including, but I think there's others as well. I mean, it's the supernova energy is like an obvious one, but I think it's more than that. It's like the precise geometry of how the gas is like lined up and stuff like that. So ideally, how I envision going forward is we have lots of hydrosims, and we empirically get the distribution of these delay times correct, and then we put that in by hand to the semianalytic models, something like that.
In your opinion?
Yeah.
Expert opinion, what came first?
I would say the star came first, because I don't consider like a halo with just a gas cloud in it a galaxy. I would call that this is just definitional, right? It's like, is Pluto a planet kind of thing, but it's, I would.
The ISM of galaxies is more than the star mass.
Yeah, so I guess if you define a galaxy as like baryons inside a dark matter halo doing stuff, then the galaxy comes first. And then the first galaxies happen basically when you get halos above the Jeans mass, where clouds can actually clump up inside the halo. Before that, if you just have naked, basically halos that can't capture much gas, do you call that a dark matter galaxy? Anyway, I don't really have, maybe Matt, you have a better.
I just want to pay you a compliment for trying so hard to make that make sense.
That's a fun question. It's like we have lunch talks at U Toledo, and somebody was talking about brown dwarfs, and I asked a similar question where it's like, you said brown dwarfs are like stars that don't go fusion, but they form like stars. I'm like, but what if they form next to a star, so they're a binary, or you have multiple brown dwarfs that are a system orbiting the star? Is it still forming like a star or a planet? And I'm like, is this a dumb question? Because I know nothing about this. And they're like, no, it's not dumb. It's like, we can argue about this all day long. So,
but I guess it's better posed if I would have asked what came first, the first thermonuclear reaction or the virialization of gas? Is that that's the way to pose it?
2 is the answer, came first. The virialization of gas. Yeah.
Before the
Yes.
first thermonuclear reaction. Okay,
Yeah.
that's the answer.
Yeah.
Okay. So galaxies.
Galaxies.
Cool. Let's thank our speaker again.